This video will introduce the basics of matrix eigenvectors and matrix eigenvalues. So we've got a matrix O here, 2 underlines indicating it's a matrix, which I've said is an n by n square matrix. So we have the vector alpha, which is going to be an n-dimensional column vector. It'll have n elements. The value omega alpha is a scalar value, which in general can be some complex number. So if we have the case where O, the matrix O times vector alpha equals the scalar omega alpha times the vector alpha, so matrix times vector equals a constant times the vector back, then we say that alpha is an eigenvector of the matrix O, and omega alpha is the eigenvalue of O for that particular eigenvector. So in general, a matrix O, being n by n, is going to have n eigenvectors and n eigenvalues. And these will be very important in quantum mechanics because in quantum mechanics, it's all about getting the eigenvalues and eigenvectors of various various functions which are often represented as matrices. Okay, so we have that. So expressing this in terms of the individual elements, we have that the sum over m, so sum over all values m, O, mn, the mnth element of O, times alpha n equals omega alpha times alpha n. So that's just the definition of matrix vector multiplication in this case, and matrix and vector scalar multiplication. So this is true for all n and all alpha. So this is true for all alpha eigenvectors, true for all n of them. So what can we write in terms of a matrix equation for trying to solve what these eigenvectors and eigenvalues are? So what we can write then, if this equation is true, is that we have O times alpha minus omega times alpha is equal to a zero vector. So this zero vector here is just that the elements of a zero vector are all equal to 0. So that's true by how vector addition and subtraction works. So a matrix times a vector is a vector. It equals a scalar times a vector. So if we subtract omega alpha from both sides, we get a 0 vector over here and omega alpha minus, O alpha minus omega alpha over here. So that's true for all of our cases. So now we can also factor this out using some clever factoring. We can say that O minus omega times an identity matrix of that size times alpha gives us the 0 vector. So you can convince yourself that this has to be true, that if O alpha minus omega alpha equals a 0 vector, that this is true as well, if these identity matrix has the same size as this O matrix. All right, so how do we solve this equation then if this is indeed the case? So the way we do that is we take the determinant of O minus omega alpha I, and we set that equal to 0, and we solve that equation. So that equation is called the secular determinant equation. Secular because it is a determinant which equals 0. So when a determinant equals 0, remember that the determinant of your inverse is 1 over your determinant. So determinant of your inverse is going to be infinity here. So we're looking for the case where we're looking for the particular value of alpha, the particular values of alpha, where this matrix O minus omega I does not have an inverse. So what that's going to do is that's going to allow us to solve for alpha. That's going to allow us to solve for omega. And once we solve for omega, then we can solve for alpha as well. So this is the basis of of a method that's called the linear variational method, which is used to approximately solve some important equations in quantum mechanics. So depending on how advanced your course goes as an undergraduate, you may or may not get to this particular example. If you're taking an advanced quantum mechanics course, you are definitely going to get to this level. So that all depends on how hardcore your professor is. So this may be for you if you're at the more extreme end of the undergrad level, or definitely if it's at the graduate or more advanced level for PChem.